I'm Marcos. I'm here to talk a little bit about the security of application installers. I think it's important to shed some light on it because many previous research work have investigated the problem of the security or the lack of security for other environments, noticeably for mobile and Android app stores, but few attention was given to desktop. So I would like to talk a little bit about that. So most people are probably used to this screen like a popular app store that you can search for an application, look to the comments, rank the applications according to their reviews. But before these applications, these app stores were popular, most of these tasks were performed by websites known as repositories, software repositories. So in the context of this work, when I'm referring to a repository, I'm referring to one of these websites. They are all very popular and very famous, with millions of downloads each one. So let's dig into them. The submission of an application, the inclusion of application in repositories, starts by someone filling a form like this and submitting it to the website administrators. So it can be a legitimate software developer trying to advertise in its creation, but can also be an attacker trying to include a malicious payload in this repository. Although all websites state that they review the application before inclusion, it's not clear which checks are performed by them and to which extent checks are performed. So maybe there's probably a security breach in some case if an attacker is able to include the malicious software in them. Even worse, the websites do not display to the user who requested a given software to be included. So maybe the users will be unaware of who uploaded that binary to that repository. What happens with this lax security policy, lax inclusion policy, is that multiple versions of the same applications will be added to the repository, as you can see here. Most of them are outdated versions of the main application, but some of them, as I highlight here, are repackaged version of the original software. So a third party decided which parts of the original software would be kept, and even worse, if additional software would be added to this main application. So there's potentially a security risk depending on what is repackaged along the software. But even worse, in addition to adding new software entries to the repositories, the binaries distributed for a given application may change over time. So in this example here, this same entry in the repository have its binary changed in March, as you can see here. So from March, the new binary started being distributed. The problem is that many repositories are not clear about that. So in most cases, the user is unaware that it's downloading a binary that's different than it has been downloaded previously. So there's maybe another security breach, another security risk, depending on which binary is distributed, or if a distinct version or even a Trojanized version of the binary is distributed in replacement to the previous, so far legitimate one. But most repositories are somehow aware that the risks of this practice, and they try to somehow prevent malicious actors and try to protect the user somehow. Like, for instance, all of them state that they check the binaries before distributing. Most of them even state that they use some popular antivirus solution to check the binaries before distributing it. But what happens in practice is that it's still possible to find Trojanization and malicious applications case. Like in the here shown example, although the software was reported as safe and secure, in fact it was Trojanized, it was infected with a malware. And here a summary of what happens in all of the repositories, and there are very interesting stuff that we need to concern about. For instance, CNET allows applications to be sponsored, which means that someone may pay for an application to climb to the first rank position. But if an attacker would be able to pay for that, to sponsor an application, what might happen is that a malicious application would climb to the first rank positions and infect multiple users. So given all this scenario that I have presented, I would like to investigate more how often it happens, how prevalent search modifications are, or more specifically, for the repositories, how often the applications climb multiple rank positions and how often their binaries are replaced, if there's still really a risk on such practice. And for the installers distributed themselves, how they are developed and if they are vulnerable to some construction. And in the last instance, if there are possible Trojanization cases. I mean, if it might happen based on this practice of the repositories, or even if they are already still happening. So I'd like to investigate all of this. And for doing so, what we did was first develop a crawler that every day collect all the most popular applications of all the presented repositories. So we collected all the binaries distributed. So even if the binary distributed for a given application change from one day to another, you are able to identify it since we collected all binaries every day. After that, we developed a clicker that is a solution that simulates the user interaction with an application. So it clicks on next, 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 as shown here, until the installation is finished with the default configuration. And after that, we executed all the download software from all these repositories in a sandbox with this clicker and collected all execution network traces, so we were able to investigate how they interact with the operating system, network, and so on. So our goal here is to present this landscape. And well, what we discovered for the repositories. Well, for all of them, we identified that we collected, as you can see in the first table here, more files, more binaries than applications, which means that all of them make this binary replacement, this binary updated over time. And more than that, the second table shows that even if the same application entry is present in two repositories, the binaries distributed by them are different. Because, for instance, they are distinct versions, some more updated than others, or some of them include third-party components that are not present in the other repositories. So in addition to often updating the binaries, these binaries are different according to the considered repository. More than that, the repositories in a general way can be described as heterogeneous. So the files distributed by them are very varied. For instance, they range from a zip file or a compressed file that is a standalone self-installer from an entire operating system distributed as an image. So as you can see here, there are a myriad of formats. But in the context of this work, we will pay attention to the Windows PE files, since they are more prevalent and more popular ones. Well, we collected all these files every day, as you can see here. So every day we collected an increasing number of binaries and distinct hashes, although in some days, as in the second figure shows, we were not able to collect some files for some repositories because many reasons, like a broken link, an unreachable server, internet problems. But in an overall manner, we do not like to point finger to a specific day or a specific repository or problem. We would like to present a landscape of what happens in general. So that's what I will present from now to the end. And the first thing that we investigated was if it was possible to an attacker to include a malicious application in a repository and make it climb the rank position, if it was possible to think in that possibility. And the first thing that we discovered, as you see in the first figure, is that for all repositories, most applications have their ranks changed. As you can see, all of them. Of course, some more than others. Like in the CNET case, the updates are more periodic than the other repositories, but all of them are daily changed most of the ranks for all applications. They are all very dynamic. And the second figure shows that although most applications, of course, climbed the few rank position, a non-negligible number of applications climbed multiple rank positions, like up to 40. So it's plausible to hypothesize that an attacker trojanizing a popular application would be able to climb this application to the first rank position, since it's the way that repositories operate, often updating their rank positions. But more than that, we also investigated if it was possible to change the distributed binary if by some means the attacker was able to control a given already existing repository entry. So as you can see here, again, all repositories daily changed the distributed binary for at least one application. Of course, some more than others, but all of them daily changed at least one application. And again, in the second figure, although most applications distributed few binaries over the evaluation period, a non-negligible number of them distributed multiple binaries. In the worst case, up to 50 distinct binaries were distributed for the same application, which seems unreasonable. At least I cannot explain why such updates is so frequent. So again, it's plausible to hypothesize that if an attacker that would be able to Trojanize a given repository, a given entry in a repository, would be able to do so, to distribute a malicious binary for a given period without being noticed, because this is the way that repository work. And since an application is distributed, it takes a very short time window until it's replaced by another one. So AV scans and analyst scans have too short period of time to investigate it. So it's plausible to hypothesize that there's a risk in this practice. But more than that, there are also problems with installers themselves. So we investigated and discovered that there are basically two types of installers, and they somehow resemble malware behavior. That's interesting because you have some implications that I will show some slides later. The first type of installer that we identified are the droppers. They are basically installers that have the payload to be installed embedded from within, and in runtime they extract this payload and install in the system. And the second one are the downloaders, that they are basically stubs that download the payload to be installed from the internet and then run the installer in the file system after download is succeeded. So basically they are a stub, and if you have no internet connection, this type of installers will not run. And well, both types of installers, both droppers and downloaders, interact a lot with the file system since they need to dump their files and reconstruct the structures they are dropping or download in order to install them in the system. So of course, most of the downloaded files are shared libraries that are required to install the software themselves, the software to run. Executable files, of course, the software being installed is probably an executable, but also a lot of temporary files, since all of them need to reconstruct these structures in the file system. These are all expected. These are non-intrusive behaviors, but there are some installers that do perform some very intrusive behaviors. So as you can see here in this code, there are some installers that even set proxy in the system, which is very intrusive because although it might have a legitimate goal, like it's downloading the software for a legitimate source, it happens that they ended up setting and modifying the proxy for the whole system operation. So the whole system is affected by this modification that was supposed to be executed only for the installation of that software. Other kind of intrusive modifications are, for example, persistent behavior. Some persistent objects are set in the system because some installers are, in fact, multi-step installers. They needed to survive reboots, for instance, to load the kernel driver, or even they need to be executed after a user login. So they implemented multi-step installers. But each one of the installers implemented its own practice. So as you can see here, a given antivirus used the default auto-run key to set its persistent to survive reboot. But another antivirus solution, the same class of solution, opted to implement a completely different operation mode. They implemented a custom routine that writes in a specific registry key, like as you can see here, there's a count. So each time that this installer is executed, for each step that it's invoked, it counts which part of the installation it is executing. So there are different implementation choices for each type of installer. And well, since most of the installers that we evaluated were downloaders, we investigated how their connection was performed, how they traffic data. And what we discovered that a significant number of them traffic data clear on unencrypted connection. As you can see here, some example. Most of them antivirus software. I don't know why they made this project decision, but most of them traffic data over unencrypted connection. And what we did was then deploy a man-in-the-middle attack against all of these installers to check if they are really vulnerable or if they implemented further measures to mitigate this possibility, like checking hashes or checking signatures in order to avoid being tampered by a extraneous payload that comes from the network. And what we discovered was that some of them really implemented some of these good practice to verify the downloaded payload, like all the antivirus solutions. They were not vulnerable, but some software were really vulnerable and thus were completely dominated by our payload offered via the network, as I will show. In this video, I exemplify an attack against one of the vulnerable applications. Instead of the expected payload, I supply the calculator as an alternative payload. We note that suddenly the calculator is open, because the installer downloaded the payload and executed it without verification. We also noticed that after closing the calculator, another instance is open, since the installer expected to execute and download multiple payloads from the internet. As a good practice, we recommend the software to verify the downloaded payloads before its execution, as shown in this another video. But well, Internet was not only used to retrieve payloads from the network, from the internet, but also used to send notifications about installation procedures to the website developers, for instance. So as you can see here, many distinct applications notified and posted tokens to the website developers to notify about the installation procedure. So they can count the number of installation, they can know which version of the software was installed and which system. So many tokens are sent by the application installers. And as important as to properly install a software is to uninstall it, to allow the user to remove the software if the software is not required anymore. But what we identified was that, in fact, a few number of applications really deployed a standalone installer, as shown in the first code here, that the user would be able to just double click and execute and remove the software. What happens in most fact is that they outsource the uninstalling procedure to a third-party component, as you can see in the second code. So a third-party component has a command line argument, for instance, to remove that other software. So it makes the user's life very hard. So most users are unaware on how to remove the software. And even us, while inspecting the application traces, were in most cases unable to identify which was the uninstaller for these applications, because this what I consider bad practice. And well, they are deployed by these third-party applications, and third-party components and applications were very popular among all of the installers. So as you can see here, they range from browser extensions to additional processes. They are run along the main application. And their implementation are also varied. So we can see that some of these third-party components are artifacts left on the file system, but some other are processors. Some of them are registry entries. So there are a myriad of implementations for these third-party components. And a common thing among them is that most of them are used to somehow fingerprint or to target the application. So as you can see here, the same software downloaded from distinct sources, writing to the same registry key, they write distinct tokens, distinct IDs to these registry keys. So we executed this experiment many times and identified that it was clear that according to the repository, there was a distinct ID. I'm not sure if they make that on purpose or if it's the only way that things work, but what happens that in practice, we are able to fingerprint the origin of each one of these installations just in looking by the token that the third-party components were deploying the system. And well, in the last instance, since we investigated lots of possibilities of adding third-party components, let's see what happens when these third-party components are somehow malicious or they are Trojanization cases. It's interesting because Trojanization is so popular to the point that some installers even report that Trojanization might occur in the software, as you can see here. Of course, this message is bypassable if the attacker wants to, but I consider this as a good security practice to raise user security awareness, since they will be aware since then that there are risks on downloading software from any source. They must check what they are downloading. And what we did to verify what's going on about organization was submitted all downloaders to VirusTotal and retrieve the detection labels and detection rates. And what I show here is that what I discovered, and is shown in the first graph, is that a 1 out of 3 of the installers were detected by at least one VirusTotal AV, which was surprising for me because I consider this rate very high. And then I investigated why the software were being detected as such. And I discovered that there are basically 2 reasons for detection. The first one is, of course, a real malware or a component that's really detected as malware by the antivirus. So like you can see here in the graph, most of them are detected as Trojan, like something embedded in the application that was not supposed to be there. But some applications also, some antivirus also detected a myriad of fingerprinting and tracking and privacy leaks. So many applications were detected because the antivirus considered that it might be risky. And a second class of detection was very interesting due to the way that the installers operate. As I've shown previously, they might be droppers or installers. And some of the installers were really reported by AVs as droppers and installers because the way that they operate was undistinguishable for the AV. So they were not able to disambiguate if the way that this software operates was a malicious installer or a legitimate installer. But well, detecting these privacy leaks is very tricky, it's very hard. So each antivirus implements a distinct policy to detect them. Some are laxer and some implement stronger policies. So as you can see here in this other figure, that among the installers that were detected by at least one AV was responsible for almost 70% of all detections, whereas another antivirus was responsible for only 5% of all detection, because their policies for detecting this tracking and fingerprinting capabilities are very different. I don't know which is better, if it's have a laxer or a stronger policy, but what I can tell you for sure is that the antivirus deployed by the repositories to scan the files was the one here in this graph that less detected samples. But well, repositories are so heterogeneous that you cannot even blame one as safer or more insecure than other, because as you can see here, each one presents a distinct detection rate. But even for CNET, that presented the largest detection rate, we cannot claim that it's insecure because there are multiple malicious artifacts in that, because what happened is that due to this binary updated procedure, the same application that was detected as malicious have its binary replaced many times, and all of them were detected as malicious by the antivirus. So the relative number of detections for such a repository has grown. So a lesson learned here is that we do not have to pay attention only to the absolute detection rate, but also in how frequent a security incident happens when we are evaluating the security of something, right? And well, going to the conclusions, there are some implications about the findings that I have presented that I would like to discuss. So for the users, the best measure for the users to be protected is to download the software from the official source, like for instance from the developer website, if they are aware of it. I know this is old, but gold, right? For the repositories themselves, if they want to keep operating the way they operate right now, with this very dynamic way of operating, they should at least pay attention to the most popular applications, because these are the ones that have the potential to climb multiple rank positions if trojanized, and so they are more prone to be targeted by attackers. And if it happens, a single binary update might affect millions of people. So they should pay attention to the popular applications at least. And for the researchers, for us as researchers, there are some implications. The first one is that many of us, myself included, are leveraging these downloaded binaries from repositories as labeled benign files for instance, machine learning procedures. So we train machine learning models using these downloaded files. There are many studies that do that. But we need to ensure to scan the files before training the models and ensure that we are not adding any malicious component like a third-party component or a tracking capability to the model. Otherwise, we are biasing the model and make it to learn that something like tracking is goodware, is a malicious, is a legitimate stuff, when in fact it might be malicious for most contexts. In addition, for those concerned about reproducibility, and myself included again, we needed not only to report that we downloaded a number of files from a given repository on a given date, we needed to make the hashes of the samples available in order to allow reproducibility, because since the repositories are updated very often, you cannot know if you are downloaded a distinct binary from the same application entry than your research partner downloaded previously. So in order to make this reproducible, you need to make the hashes available so you can run the experiment on the same binaries, right? And now I think this subject of application installers is very interesting. And I think this work does not stop here. There's a lot of things to do by us and many researchers, because the scenario is changing very often, very fast. So as you can see here, Microsoft deployed an app store for desktop applications. So you can download for your Windows applications now, not from repositories, but from the official Microsoft application store. So there's a lot of possibilities to enhance this, to include security practices and measures to it. So I think if other vendors and providers move to the same model of operation, there's a lot of potential measures that we as a researchers can take to help them. And I think there will be many research possibilities to be explored in the future due to this. And well, that was it. Thanks for watching me until here. You can reach me by email or on Twitter to make any questions, and thanks a lot.